Well, guys, the internet's still out. It's 9:50, and the temperatures went way up. The ground is still, yeah. And I forgot to mention, this is, I think, yeah, there's 12 inches between these, so it's 2 feet. And the whole width of the compost is 4. So 1 foot here, 1 foot here, and there's really half-inch plywood there, so that's not going to provide much of a insulation. So that's why um, these sides are cooler than the middle, and this is exactly middle. I mean, 2 feet from here and 2 feet from the other side, and the middle of the pile, because these sensors just under, maybe an inch or two under the top of the compost, and these are touching the ground. See, this one never got up to, you know, big temperature. I'm thinking there's some kind of drainage over there, or somehow. Uh, well, actually, this one, it's right next to a tree, so there's a big root, like a surface root. It's like 3-4 inches diameter. This is actually on top of that one, so it's not necessarily touching the soil, and these are just above the soil because of that. So, but regardless, so as I mentioned in the previous video, and you can see the temperature, and you see these empty spots vertically. Something's happened. It's either Wi-Fi is dropping off, because it's inside the compost. There's a tree, and there's a azalea tree, and then a big tree trunk next to it, and you know, other than that, it's should be line of sight, but somehow it's dropping. It could be the service too. I put all kinds of messages when things go bad. I didn't see anything. So, okay. The problem was, if you ignore those non-datas, it stops here 7:58, and yes, like for 6 minutes it stops. I mean, who knows? Anyway, so let's zoom into somewhere like this, and you can see it's oscillating. My intuition was that this was caused by the distance. So these are distant too. However, the change is not that much. It's 34.6, 32. So 2.6 volts. And this is L5, R5. The middle one, and that's left. So it's not like a line, same uh, column, so to speak, because L4 is also having problem, and L1 is, you can see, closest to the surface, also to the board. It's like almost flat. So it's combination of both the cable length and sensor. So even if I have the same sensor, MCP9700A, in two different packages. I have, in this case, what we have in the circuit is surface mount package. So I also have through hole package, which is bigger plastic package. So it should be theoretically, I guess, a little bit more durable, and but essentially the same thing. So what I'm planning is, I've been looking at what the frequency is. I kind of say the period is about 30 seconds. yeah, it's 938.55, 939, and 939.31. So it's a 30 seconds period it oscillates, and other ones also does the same thing. So regardless of what's causing it, we can remedy it by filtering. Well, by buffering. Apparently the sensor, temperature sensor, is not able to, you know, supply this voltage pushing 40 inches. It's really like M5 is 40. M5 is not really 40, it's just like 27 and a half, because the middle one is straight going in and the left and right goes up and into the middle circuit. So the L's actually longer, but this makes no sense. It may have to do with the temperature. Higher the temperature, more the oscillation, but that makes no sense either, because it was oscillating. Regardless, we can stop its oscillating by first buffering, excuse me, and then perhaps filtering. So this is the video that I've been, since I don't have no internet, and literature from school, and some papers I saved up previously. This is math heavy, but I mean you don't really have to, because I found in Wikipedia through my phone, because I can't show it in here because I don't have internet, but the phone has. So um, there is a certain case. Well, first let's back up. Okay. So I have been looking at this document mainly, and then I stumble upon this Sallen key, which I use Sallen key topology. It is a second order low pass filter, and this happens to have no gain. So whatever voltage coming in, it's filtering it. It's no multiplication or anything, just as it is, but it's filtering it. So this one is there's a gain setting through the resistors for the operational amplifier. So the math on this is kind of, as shown here. There's a transfer function, blah 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 blah, and then I don't think, and it goes to Chebyshev low pass filter, which is, yeah, but this is simple, not this form, but the what I found on Wikipedia. If you have a certain relationship between resistors 1 and 2, and the Wikipedia example actually had this as, oops, this as C2, this as almost C1, and this is C2. So that's when it says C1 in here, that's actually this one, and if it's C2, if it's C1, it's C2. So there's a relationship. So you have an M and R as like generic resistance. So R2 becomes, if if you use these values, in this case it's R2 divided by M, and then in this case M times, well, I'm sorry, R times, well, this one is R divided by M, and the R1 is M times R. And it's similarly for C2, we have C divided by N, and C1 is N times C. If you keep this format, you know, the components are, and there's actually another. I shouldn't, if I had internet, I wouldn't be doing this. I'd be working or doing something else, but I can't show that document. It's in the Wikipedia, the selling key topology. If you type it in there, it'll show. This is a shortcut, and Q is the like quote unquote quality, whatever. Uh, Lower this, the number, better the filter is, and then through this, actually, you can the calculation of the cutoff frequency. It calculates frequency. It's basically 16 um, millihertz, which is about 62 seconds. We'll find out in a second, but actually 30 seconds, not 62 seconds. Well, 60 seconds. Yeah. I think it's 15.915. Simulate again. Yeah, 62, 63 seconds is the period. But I'm doing twice as much to do a better filter. Anyway, we'll get to that. Let's put that back to 33 millihertz. It's just 30 seconds roughly. The period. Let's do single capture. Yeah, from here to here is 30. It's 20 seconds. Yeah, from here to here is 30, which is what I see on the other one too. We'll get to this in a second. Okay, so first of all, what is low pass filter? Low pass filter, it's simple names, low pass filter. So you pass the frequency component of a signal, signals with frequency lower than certain frequency. So you're ignoring high reject filter, low pass filter. Yeah. There's also high pass, band pass, and band reject. And I believe this document kind of shows, nah, that doesn't show that. This does probably. Yeah. Okay, orders. Okay, let's zoom out a little bit. Okay. And this is by, well, this is by Texas Instrument too. What the heck is this called? Active low pass filters. It's a specific one. This one is active filter. And this is on SLOA 088. They got numbers to these things. SLOA 040. This is an earlier one. That's more specific, but yeah. Anyway. Let's see. This does not show, and I don't have internet to show you. Okay, for instance, no, that's an overshoot. It's not. Okay, so this is a band pass filter. This part, like this is the frequency, and this is the gain. Zero gain is the same. Signal pass is the same, and this is a logarithmic scale. And the negative gain in dB, well, regardless of dB or whatever, negative gain is loss. Basically, you're losing the signal, or signal being dissipated, or being ignored, or being filtered out. So this is low pass. It passes the low ones as it comes to a frequency where the signal is 3 dB. Basically, it is a half the amplitude of the signal. That's the cutoff frequency, and I think it's about right here. So that will be the cutoff frequency for that. and you want this to go sharply down, ideally. But yeah, good luck without introducing all kinds of craziness. So it's gonna gradually go off. So that's what I was saying. I was setting it up for a worst case. So the um, the response would be much better. So it would start going off earlier, so ignores more of the frequencies and faster frequencies and faster than that frequencies, much faster earlier as the frequency goes up. So, and with the help of this thing, I basically came up with, well, actually I'm going to do 220 microfarads. So the frequency is going to be, well, that's, I don't know, 1 over 0 0.007234. It's 138 seconds. A change that would be happening 138 seconds. But mine is actually doing it in 30 seconds. So it's cutting anything faster than this. Trying to, it's tapers off like this. So instead of doing this, I do this. By the time it gets to that frequency, it's already 30-40 dB below than the original signal amplitude. So it's filtered earlier on, which is fine. I mean, the only thing is the capacitor value gets larger, and this is at 1,000. I mean, 1,000 or 100,000 kilo ohms, which is kind of the limit for this type of stuff. I think it says it over here somewhere. Oh, don't use this, blah blah blah. I read the whole thing. I think not this one, probably. Yeah, this low. Yeah, I think it says over here. Caveat or capacitor selection. Yeah, got the tables. Says component values. There you go. Yep, there you go. Come on now, zoom. Unbelievable, zoom. Why not? Okay, the upper limit 100K to avoid excessive resistor noise. So yeah, it's kind of, I just put. But there's also limit. Well, I don't think there's a limit to the capacitor, but yeah, whatever. I don't want to do it. Okay, so let's go back to this, and I already designed on simulation Multisim. This is what we had in school. It's yeah, 2013. Yep, 7 years ago. Well, I'm still simulating. Okay, so I just put this in here as a buffer. It basically, receives the. This is not a temperature sensor, but imagine it is. It's set up in a certain way. It simulates what we had on the actual data, and the variation is as same. So peak to peak was 50 millivolts. Well, see, there's something when you say peak to peak here, it's actually amplitude for some damn reason. But it's actually 50, and there's 5 degrees, 10 degrees, 10 millivolts per degree, so 5 degrees, and we were looking at earlier, and the oscillation was 5 degrees, so it was 50 millivolts basically in voltage. So what this does, buffers it. So this, if this has only certain whatever the current it can push through, this operational amplifier it does not require much current into its terminals. I know this is high level, not high level, it's more technical, but just trust me, what this does, it takes exactly the same voltage but and puts it out here to feed to the other op amp in the cell and key configuration in a way that this is capable of driving more current, which is not necessary because the values I use so high resistance. I think this is redundant, so may not need it. But yeah, I don't have internet, and I had to look into my phone and search on that tiny screen for an operational amplifier, single operational amplifier on, you know, electronic distributor. It just kills me, that small screen. Anyway, since one that I thought of, the one that I have, has two operational amplifiers in one package, 8-pin package. This comes as a bonus already anyway. Might as well just use it as a buffer to feed into this. So this is the topology for the cell and key, and I'll be supplying 5 volts, and the temperature sensor thing will also use 5 volts too, and so 100 kiloohms, and then 220, just as it is. And I'm graphing, well, using the scope function, input, whatever the simulated temperature variation in yellow, and channel 1, which is yellow, and then the output of the system as V out, which is going to the second channel, which is blue. As you can see, at this frequency, single, okay, that's going crazy, but I'll just single shot it. Come on, there you go. So what happens here is it's exactly the same situation we have, which is 50 millivolt oscillation at 33 millihertz, which is, it happens every 30 seconds, and the output is not gonna follow that. Right now we're reporting the yellow one, and that software that I been showing the temperatures. Yeah, it's just like, oh, so that's what's coming directly. But now we have the output is 25 times almost at this frequency, which is what I want to design for. The change in peak to peak is 25 times less. So in other words, in 30 seconds the perceived temperature change will be 0.221 degrees. So it will be much more stable. It will still wiggle just like it's doing over here, but the graph and the everything, it will be more smooth. Also, this temperature, this bacteria generates the heat, and the temperature rise. It doesn't happen immediately, really suddenly anyway. So this is what this calculates is the half amplitude. This is the 3 dB point. So if I set this to I think it was 72345, well, that diesel dumbass, oh well, 7234, okay, millihertz, 7.234 millihertz, and then 6, and if I run it, it's going to be half. This is 50 millivolts peak to peak, and then the output will be 25. That's theoretically what it should be. All the calculations, the values put in here. Well, I need to run and single. There you go, 24.9. Well, pretty close to 25. So what it is low pass. So our frequency is getting lower and lower and lower, and signal is going through more and more unchanged. Well, there's this phase shift in here, but I won't get into that. There's just, yeah. I mean, it can be calculated. It's just, yeah, whatever in here. Yeah, I won't get to that level. So I don't care about the phase shift. So, and this, as I was saying, is 138 seconds period. So if there was 138, if there was a change like this in the actual sensor, 138 seconds, that would reflect a little bit better. So if I go like 1 millihertz, so once a thousand, like it takes 1,000 seconds, I think it fails in here. Well, no, it doesn't fail. Hold on. Yeah, it's I don't think I can zoom anymore. Like single shot, but it is almost. You can see from the graph, uh, it's almost passes as unchanged. So very slow changes goes through, and really fast changes. Like I'm gonna do it 1 hertz, like once a second. It changes 5 degrees Celsius. So 1 hertz would be it will be in well it will be insignificant. Let's just find out. Yeah, there you go. Yeah, like not even zero point 0.1 millivolts. I mean, yeah, 0.1 um what you call hold on a second. Yeah, well, now it's correct because I'm like, what the hell? No. Yeah, it's uh 2 thousandths of a uh 2 thousandths, I think 2 thousandths of a point one, 2 thousandths of a degree. Yeah, in 1 second. It can only change that much because of the filtering. And if you do like anything higher than that, like I don't know, 1 kilohertz, also forget about it. Yeah, yeah, it's nano. Yeah, it's like it's in one like point uh, 0.2 millionth or whatever. It's insignificant. So let's go back to our design. Oh my God, stop this and start it. So let's go back. Oh, we're going correct. All right, there you go. Single shot. So in the design, what we saw, it drops 5 volts, well, 5 degrees, 50 millivolts in 30 seconds. Well, it comes back to, so it's going to work. Yeah, so it basically switches only 0.221 Celsius. Um, well, I can design this and send it out, but it will take space. How the design is going to change accordingly, and how let's see, last 62.1. Good job, and it's still collecting. So it's as you can see, it's gotten hot. Like this is midnight yesterday. This is it's almost, yeah, it's 22 hours. Let's say it's kind of stable in here. So what is this, 4 5 o'clock, because sun was going down, and it was getting cold, kind of compensating for the you know colder outside. It's not gonna get that hot. It's starting to pick up here because what I did, well, I can't show like that, it's not apparent. So it's picking up a little bit over here because I think I went outside and turned off the uh, air circulation, because colder the air outside, and it's gonna pump the air in there. It's gonna cool everything, which I may want to do it, but not at this stage. I want it to get hot as hot as possible, um, because uh, I want hotter it is, more bacteria there will be. Because I know for a fact I put crap load of chicken feed food, and it's moist enough, and there should be enough air, because the material I've been using for this one is pretty coarse, so there's a lot of air pockets in there, so there's oxygen, moisture, and food. So keep multiplying. So I want to keep it warm at this time. Besides that, and you can see that in what this is 17, let's say 17. I got here, well, still not, there you go. Let's say 5 o'clock start. Okay, 17 hours. It took 17 hours to go. This is 61.6, and it came from here. So 30 degrees, 31 degrees, or whatever, 32 degrees. It took 17 hours. So it's a gradual change. And I can do extremely low pass filter and ignore all this craziness over here. Look at this yellow one, unbelievable. Look at that. 40.1, 35.9. It's like, wow. 4.2 degrees, and there's actually, it's even higher. Yeah, look at that. 40.1. Well, it's similar. Yeah, that's almost the same thing. It looks different. So 35.1, 42. Yeah, that's, but there is a certain frequency to it, and then it's about 5 Celsius. It changes. So hopefully 62, 62.7. See, this is getting slightly hotter because there's no more, it's in the bottom, but yeah. So let's see. Yeah, this should work as the numbers saying. Oh, well, don't get me wrong, I don't trust these numbers, but the circuit is simple enough. Because this burnt me before. It's theoretical is never same as the actual reality. In fact, I can't do a transient analysis for this because it just, yeah, it just craps out for some reason, and it says like, oh, time calculation did not work. Well, I'll put it, you know, put it on a breadboard and test it before I send it out. Plus, all the, you know, designing is a whole thing. You know, I need to let's see. This thing, you know, how that design will be. I need to, it's a chicken and egg problem. If I make the, you know, it shouldn't be inch thick. It's gonna be hard to put it, especially three times the resistance all at the same time into the compost. So I need to keep it small, and I'm going to make this thing so simple this time. It will be able to be pulled apart and put it back together. No hard soldering or no. So I'm gonna have to work on that, and that is gonna drive the size, because I don't want to, you know, these boards were containers and copper. Yeah, these boards, get the booms out. It's just, yeah, it's pretty narrow, you know, 0.17 inch by 1.378, and then metric would be 4.31 and 34. So this is actually the long one. This the other ones. These ones are smaller. Same width, height is like 18, so it's half the size of that. This time everything will be uniform because I won't be messing around, because it's going to be modular, easy to put it on, so I think I can get away with it. This will not change, and I don't intend to, doing filter for this one. It's right here. It's mainly the length of the, I'm just doing filtering just to be doing filtering, yeah, whatever. So, chicken and egg problem. I don't want this thing to be huge, so I can, therefore I wouldn't be able to penetrate it into the compost easily. And at the same time, I'm narrow, very narrow, and it's fitting. I can fit this stuff no problem, but it's just pain. So I'll keep you guys posted for the design and how it's going to be implemented. I'm kind of worried about this being too high, and then these are being, well, I mean, frequency is really low, so I guess that's what I need. Anyway, so yeah, I didn't work today, but work on this and help neighbors out, well, tiny bit, and finish the yard. My yard is completely finished now since hurricane. No debris, well, very small debris in between grass, and I'll probably pick those up with the mower, hopefully. Yeah, everything's in order. I'm just waiting for freaking Cox to come here, and I called them, and they're still saying no estimate on time of repair. It's like, how do you not know? No estimate means it will never be fixed theoretically, like, because you have, apparently, you don't know what it's either you don't know where it is, you don't know what's wrong, or you don't know how to fix it. Hopefully none of those are applicable here, because it's unbelievable. How can you not have, like, even if you order the parts from China, there's a rough, on the other side of the world, not because China, just takes 30 days, right? There's a rough time frame, and let's say you put it on in a couple days, or 32 days. Heck, they say 35 days. That's as long if my internet is off 35 days. I don't know. I'd be extremely unhappy. But I'm saying, how do you not know? How do you not have any estimate? It's just anyway. So hopefully I'll be done with this before the power or whatever the internet comes back on. Otherwise, I'm gonna get really good at filtering. Anyway, so you guys have fun, and if I come up with something, I'll let you know. Thanks for watching. Bye.